Hello. So, this is literally everything there is to know about topology. So, as you fall asleep or just relax, we are gonna go through everything, the entire history, how it works, from the simplest concepts to the hardest ones. And at the end, we are gonna once again look at some theories and predictions for the future. A lot of you were also asking for some research to back this up, so everything I read to learn about this before making this script is in the description. But without further ado, let's begin with topology. So there's this city. It doesn't exist anymore, not in the form it used to, but back in the 1800s it was called Konigsberg. It sat in what was then Prussia, and it was the kind of city that people actually walked around in, the way you do when life is slower and the main entertainment is a good stroll. The city was built on and around a river called the Pregel, and the river split into two branches that wrapped around a big island in the middle. Connecting all of this, the island, the two river banks, all the different pieces of land, were 7 bridges, and people in Königsberg had a question. It sounds almost too simple to matter. They wanted to know whether you could walk through the whole city, crossing every single one of those 7 bridges, but crossing each bridge only once. That's it. That was the question. Not a question about war or trade or survival. Just, can you do this walk? Nobody could figure it out, not because they weren't trying, but because nobody had the right tools to think about it. And that's what makes this story matter, because solving this one annoying local puzzle eventually cracked open an entirely new branch of mathematics. A branch that has gone on to shape how we understand the shape of the universe itself, how we build quantum computers, how we study cancer, and how we think about reality at the deepest level. That branch is called topology. Topology is the math of shape without measurement. It's the study of what stays the same about a thing even when you stretch it, squeeze it, twist it, fold it, as long as you never tear it or glue parts of it together. You've probably heard the famous line, "To a topologist, a coffee mug and a donut are the same thing." And that's true. They both have exactly one hole, so in a topological sense, they're identical. But that one-liner undersells how deep and how strange this subject actually gets. Because once you follow topology all the way down, you're talking about the shape of space itself, about mathematical objects that can't exist in our universe, about a proof so hard it took 100 years to crack, and when someone finally did it, they turned down $1 million and a Fields Medal. Let's start at the beginning. The year is 1736. A Swiss mathematician named Leonhard Euler, and if you've done basically any math at all, you've met Euler because his name is on everything, is asked about this Königsberg Bridge problem. Euler is the most productive mathematician in history. He wrote so many papers that even after he went blind, he kept churning them out by dictating them. The man was an absolute machine. Now here's what's interesting about how Euler approached this bridge problem. Everybody else had been thinking about it geometrically, thinking about the actual distances between the bridges, the layout of the river, the physical map of the city. Euler looked at it and said, the distances don't matter. What matters is the connections. Which pieces of land connect to which bridges, and that's all. So he stripped out everything that didn't matter. He turned the islands and river banks into points, and he turned the bridges into lines connecting those points. He made what we'd now call a graph. And then he asked, given this pattern of connections, is there a path that traverses every line exactly once? He worked it out, and the answer was no, not for Konigsberg. He showed that for a graph to have that kind of path, what we now call an Eulerian path, every single node except at most two of them has to have an even number of edges coming out of it. In Konigsberg, all four of the land masses had an odd number of bridges connecting to them, so no such path exists. Done. Now, why does this matter for topology? Because Euler wasn't just solving a puzzle. He was recognizing, maybe for the first time in the history of mathematics, that some problems are purely about shape and connection, not about length, not about angle, not about anything you could measure with a ruler. He even called his approach geometry of position, which was his way of gesturing at something he could feel was different from regular geometry, but didn't have a name for yet. That paper from 1736 is usually called the birth certificate of topology, and also of graph theory, which is a whole other story, but Euler wasn't done. A few years later, in 1752, he found something else. He was looking at three-dimensional solid shapes, things like cubes and pyramids and prisms, and he noticed a pattern. If you take any of these shapes and count the number of vertices, the corners, the number of edges, and the number of faces, and you calculate vertices minus edges plus faces, you always get 2. For a cube, 8 vertices, 12 edges, 6 faces. 8 minus 12 plus 6 equals 2. For a tetrahedron, 4 vertices, 6 edges, 4 faces. 4 minus 6 plus 4 equals 2. Over and over again, always 2. Euler published this formula. He was thrilled by it. And today, we write it as vertices minus edges plus faces equals 2, and we call the resulting number the Euler characteristic of a shape. It's one of the great topological invariants, a number that captures something deep about the shape of a surface, a number that doesn't change no matter how you deform that surface, as long as you don't punch new holes in it or fill existing ones. Euler couldn't prove it completely at the time. His proof had some gaps and assumed the shapes were convex. But the formula was right, and it opened the door. A Frenchman named Antoine-Jean Lullier walked through that door in 1813. He was reading Euler's formula and he noticed something. What happens when you have a solid with a hole in it? Like a donut shape, the formula breaks down. For a solid with one hole, a torus, the Euler characteristic is not 2, it's 0. For a solid with 2 holes, it's -2. Lullier was the first person to notice that the Euler characteristic changes depending on how many holes a surface has. He had stumbled onto the first known example of a topological invariant, a number that tells you something real and unremovable about the shape of an object. That number, the Euler characteristic, would become one of the most important ideas in all of topology. For the next several decades, topology developed slowly and mostly as a side effect of people trying to understand other things. Geometry was getting weird. Carl Friedrich Gauss, another one of those guys whose name is on everything, was working on curved surfaces in the 1820s. and he noticed that certain properties of surfaces could be described entirely from within the surface without reference to the space around it. This sounds philosophical, but it's actually huge. It means the geometry of a surface is intrinsic. You could figure out whether a surface is curved without ever stepping outside it. Then Bernhard Riemann came along in the 1850s and absolutely blew the doors off. Riemann was Gauss's student, and he had this unreal spatial intuition. He was thinking about complex functions, functions that take a complex number as input, and he realized that these functions live most naturally not on a flat plane, but on surfaces that wrap around and have multiple layers. He invented what we now call Riemann surfaces, and studying them required thinking about the topology of these surfaces, how many holes they had, how they connected up, what loops you could draw on them. Riemann was one of the first people to really look at surfaces as global objects. Before him, people worked locally. You'd zoom in on a tiny piece of a surface and describe what it looked like near one point. Riemann said, "What does the whole thing look like? What are its global properties?" That shift in perspective from local to global is one of the defining moves of topology. Then, two Germans came along with objects that genuinely broke people's brains. In 1858, August Möbius, yes, the Möbius strip guy, described the surface with only one side. You take a long strip of paper, give it a half twist, and tape the ends together. Now, if you start drawing a line down the middle, you'll cover both sides of the paper and come back to where you started. The Möbius strip has only one side and only one edge. It's a no-orientable surface, meaning there's no consistent way to define inside versus outside on it. Felix Klein took this further in 1882. He constructed the Klein bottle, which is a closed surface, no edge, no boundary, that is also non-orientable. The Klein bottle can't actually exist in three-dimensional space without passing through itself. You need at least 4 dimensions to embed it properly. It's the kind of object that makes you realize that the space we live in isn't the only space that's possible. These objects weren't just curiosities. They were the beginning of the systematic study of surfaces. The question became, given all possible surfaces, how do you tell them apart? How do you classify them? This question is now completely answered, and the answer involves exactly 2 things. How many holes a surface has, its genus, and whether it's orientable or not. Around the same time, a man named Georg Cantor was building something that topology would eventually need desperately: set theory. Cantor was trying to understand Fourier series, ways of writing functions as sums of sine and cosine waves, and he kept running into these weird, complicated sets of points where things would go wrong. To understand those sets, he invented the machinery of set theory. Cantor introduced concepts like infinite sets, cardinality, limit points, open sets, and closed sets. His contemporaries thought he was insane. Leopold Kronecker, another mathematician, called him a corrupter of youth. The Catholic Church had opinions about his ideas on infinity. Cantor spent years of his life dealing with depression and institutionalization, at least partly because the mathematical establishment of his day rejected what he was doing. He died in a sanatorium in 1918. But his ideas were right, and they were exactly what topology needed. Because eventually, once mathematicians started trying to build a rigorous theory of continuous functions and limit processes, the very core of what topology is, they needed Cantor's language. Open sets, closed sets, limit points, sequences, these became the alphabet of the subject. In 1894, a German mathematician named Johann Listing published something that actually coined the word topology, from the Greek topos, meaning place, and logos, meaning study. Listing had been thinking about these ideas for decades, and he wanted a name that captured the study of position and connection rather than measurement. Topology, place study, it stuck. But the person who really launched topology into orbit, who gave it wings, as historians of math sometimes say, was Henri Poincare. Poincare was French, born in 1854, and he is one of the last people in history you could genuinely call a universal mathematician. He worked on everything: celestial mechanics, complex analysis, differential equations, physics. He was the person who came closest to discovering special relativity before Einstein. He was a legendary lecturer and science communicator. He thought about thinking, writing essays on mathematical intuition and the psychology of discovery that are still worth reading. In 1895, Poincare published a paper called Analysis Situs, Latin for Analysis of Position. This paper is considered the founding document of modern topology. It wasn't just a paper, it was 6 papers published over the next 9 years, each one building on the last. Poincare wasn't just doing topology, he was inventing the tools for doing topology. One of those tools was something called the fundamental group. Here's the idea. You have some topological space, some surface or higher dimensional shape. You pick a point on it. Now you consider all possible loops that start at that point, go somewhere on the space, and come back. Some of those loops can be shrunk down to a single point. You can deform them continuously until they collapse. Other loops can't be shrunk. They're trapped, going around some hole that they can't escape. The fundamental group captures this. It's a group, an algebraic object, made up of the equivalence classes of loops. 2 loops are equivalent if you can deform one into the other. The structure of this group tells you something deep about the shape of the space. For a sphere, every loop can be shrunk to a point, so the fundamental group is trivial. It just contains one element, the identity. For a torus, the donut shape, you have 2 independent types of non-shrinkable loops, one that goes around the hole and one that goes through it. So, the fundamental group of the torus is richer. Poincare also introduced homology, a way of counting holes of different dimensions systematically. A 0-dimensional hole is just a disconnected piece. A 1-dimensional hole is a loop that can't be filled in, like the hole in a circle. A 2-dimensional hole is an enclosed cavity, like the inside of a hollow sphere. Homology groups capture how many of each kind of hole a space has. And then, in 1904, at the end of one of his papers, Poincare asked a question. He didn't even frame it as a conjecture. He just wondered out loud. He had been thinking about 3-dimensional spaces, not surfaces, but full 3-dimensional manifolds. spaces that locally look like ordinary three-dimensional Euclidean space, but might be globally different. He asked, if such a space has the property that every loop in it can be shrunk to a point, meaning its fundamental group is trivial, does that mean it must be a three-sphere? A three-sphere is the three-dimensional analog of an ordinary sphere. Just as an ordinary sphere is the set of all points in three-dimensional space at a fixed distance from a center, a three-sphere is the set of all points in four-dimensional space at a fixed distance from a center. It's the simplest, most symmetrical, most well-behaved three-dimensional manifold. What Poincare was really doing here was asking, is the three-sphere uniquely characterized by its fundamental group? In two dimensions, the answer was already known. A simply connected closed surface is a sphere, but in three dimensions, Poincare himself had earlier made an error. He thought a weaker condition was sufficient, then constructed a counterexample to his own claim, the Poincare homology sphere, which has the same homology as a tree-sphere but a different fundamental group, and then posed the corrected question. The Poincare homology sphere is itself a fascinating object. It's a three-manifold with the same homology groups as the three-sphere, but a non-trivial fundamental group, specifically the binary icosahedral group, which has order 120. It turns out to be related to the icosahedron and to one of the exceptional Lie groups, the one mathematicians call 8. These connections across different areas of mathematics, topology, group theory, and symmetry are typical of the way topology operates as a meeting point. That question became the Poincare conjecture, and it was the central unsolved problem in topology for the next 100 years. While people were sweating over the Poincare conjecture, the rest of topology was getting built out. The early 20th century was when the subject got its rigorous foundations. Maurice Fréchet introduced metric spaces in 1906, spaces where you have a well-defined notion of distance between points. These were a generalization of Euclidean space, and they turned out to be the right setting for a huge amount of analysis and topology. Felix Hausdorff in 1914 went further. He defined what a topological space should be in general, without necessarily having a distance function. His definition used neighborhoods. For each point in a space, you specify which neighborhoods of that point are allowed. The neighborhoods have to satisfy certain axioms. They have to be well-behaved, overlapping in sensible ways, but otherwise the space can be almost anything. Hausdorff's definition gave topology its modern foundation. A topological space, in his setup, is just a set with a collection of open sets, subsets that represent the neighborhoods, satisfying three simple axioms. The empty set and the whole space are open. The union of any collection of open sets is open. The intersection of any finite collection of open sets is open. That's it. Those three axioms are the bedrock. Everything in modern topology, continuous functions, homeomorphisms, compactness, connectedness, limits, convergence, everything is built on those three axioms. It's almost insane how much you can build from something so simple. Kazimierz Kuratowski, a Polish mathematician, cleaned this up a little in 1922, giving us the version that's taught today. And then Georg Cantor's set theory, which had been dismissed by so many of his contemporaries, turned out to be the exact language needed to express all of this. Cantor was vindicated posthumously. So let's actually understand what's going on here. Let's get into the guts of topology. A topological space is, loosely speaking, a set of points with some notion of closeness, not distance, just closeness. You don't need to be able to say these 2 points are exactly 3 units apart. You just need to be able to say this point is close to that region. The open sets are the way you encode that closeness. Here's an example. Take the real line, just all the real numbers laid out from negative infinity to positive infinity. The open sets are things like open intervals, the set of all numbers between 0 and 1, not including the endpoints, or the set of all numbers greater than 5, or the union of multiple such intervals. You can specify which subsets are open, and as long as your collection satisfies those 3 axioms, you've got yourself a topology. Now you can ask, what does it mean for a function to be continuous in this setting? It means the preimage of every open set is open. If you take an open region in the output space and pull it back through the function, you get an open region in the input space. This captures the intuition that a continuous function doesn't have jumps. It doesn't suddenly teleport you from one place to another. 2 spaces are called homeomorphic if there's a function from one to the other that's continuous, 1 to 1, and whose inverse is also continuous. A homeomorphism is a topological equivalence. If 2 spaces are homeomorphic, they're the same space as far as topology is concerned. The coffee mug and the donut are homeomorphic. The sphere and the cube are homeomorphic. A circle and a square are homeomorphic, but a circle and a figure 8 are not homeomorphic. If you remove 1 point from a circle, it stays connected, you get a line. If you remove the crossing point from a figure 8, it falls apart into 2 separate arcs. Removing a point from one gives a different structure than removing the corresponding point from the other. That's a topological difference. This idea that you can tell spaces apart by seeing what happens when you remove points or cut along curves is one of the basic tools of topology. And then there's the separation axioms, a hierarchy of conditions you can impose on a topological space to make it more and more nice. The weakest level, called Kolmogorov or 0, requires that for any 2 distinct points, there's at least one open set containing one but not the other. The next level up means every singleton, every set containing just one point is closed. The Hausdorff condition, the level after that, means any 2 distinct points have disjoint neighborhoods. You can fully separate them. The regular and normal conditions go further, separating points from closed sets and closed sets from each other. Most spaces you'll encounter in practice are Hausdorff. The reason Hausdorff spaces are so important is that sequences have unique limits in a Hausdorff space. You can't have a sequence converging to 2 different limits at once. Without Hausdorffness, all sorts of pathological things can happen. There are also paracompactness and countability axioms. Second countable spaces have a countable basis, meaning countably many open sets from which all others can be built. This is satisfied by the real line, by Euclidean spaces, by most manifolds you'll meet. It's a strong condition, but widely satisfied. Morison's lemma, a theorem from 1925, says that in a normal topological space, any two disjoint closed sets can be separated by a continuous function. It's one of those results that sounds technical but turns out to be used everywhere. Tietze's extension theorem says that a continuous function on a closed subset of a normal space can be extended to the whole space. These are the workhorses of general topology. The Tychonoff theorem says that the product of any collection of compact spaces is compact. This is proved using the axiom of choice, specifically Zorn's lemma, and it's actually equivalent to the axiom of choice. This was proved by John Kelly in 1950. The Tychonoff theorem is used constantly in analysis and topology, and knowing that it's equivalent to such a foundational set theoretic axiom is both surprising and a little unsettling. Now, compactness. This is one of those concepts that sounds technical but is extremely useful. A space is compact, roughly, if it doesn't go off to infinity and doesn't have any missing points. The interval from 0 to 1, including its endpoints, is compact. The real line is not. It goes on forever. An open interval from 0 to 1, not including the endpoints, is also not compact because the endpoints are missing. Compact spaces are nice because continuous functions on compact spaces are well behaved. If a function is continuous on a compact space, it actually achieves its maximum and minimum values. It can't just get closer and closer to something without ever reaching it. Then there's connectedness. A space is connected if you can't split it into two separate pieces, both open, both non-empty. A line segment is connected. Two disjoint circles are not. You can split them into two pieces. The rationals are totally disconnected. Between any two rational numbers, there are irrationals, and the rationals fall apart into tiny pieces. Path connectedness is stronger. A space is path connected if you can draw a continuous path between any 2 points. For most reasonable spaces, path connectedness implies connectedness, though the converse is famously false for some weird examples. These are the basic concepts of general topology, also called point set topology. It's the language layer, the grammar of the subject. You need it, but it's not where the action is. The action is in the more specific branches. So let's talk about surfaces, because surfaces are where you start to see topology get interesting visually. A surface is a two-dimensional manifold, a space that locally looks like a flat plane near every point. Surfaces can be finite and closed, like a sphere, finite with boundary, like a disk, or infinite, like the full plane. The closed surfaces, the ones with no boundary and finite extent, are the ones that get classified completely. The classification theorem for closed surfaces is one of the great theorems of mathematics. It says, every closed orientable surface is homeomorphic to exactly one of the following: a sphere, a torus donut, a double torus, a shape with two holes, a triple torus, and so on. For any number of holes, the number of holes is called the genus of the surface. Two orientable surfaces are topologically equivalent if and only if they have the same genus. If you include non-orientable surfaces, surfaces like the Klein bottle that don't have a consistent notion of inside versus outside, then you also need to track that. Every closed non-orientable surface is either a real projective plane, or a Klein bottle, or a connected sum of more projective planes. That's it. That's the full list. Every possible closed surface, completely classified. What's the Euler characteristic got to do with this? Everything. For an orientable surface of genus G, the Euler characteristic is 2 minus 2 times G. Sphere, genus 0, Euler characteristic 2. Torus, genus 1, Euler characteristic 0. Double torus, genus 2, Euler characteristic -2. The Euler characteristic is a number that encodes the topology of the surface in one integer, and crucially, the Euler characteristic is a topological invariant. No matter how you triangulate a surface, no matter how you cut it into polygonal pieces, the formula vertices minus edges plus faces always gives you the same number. That's a theorem, and it's one of the most beautiful results in low-dimensional topology. And then there's the connected sum operation, which is the topological equivalent of gluing. You take two surfaces, cut a small disk out of each one, and glue them together along their boundaries. The result is a new surface. You can build a double torus by taking the connected sum of two tori. A triple torus is the connected sum of 3. All the higher genus orientable surfaces come from taking connected sums of tori. The classification theorem tells you that this gives you everything. Every closed orientable surface is the sphere, or some number of tori glued together. That's the whole list. It's a theorem from the 1900s that's been proved in many different ways, and it's one of the cleanest classification theorems in all of mathematics. There's a completely equivalent reformulation. Every closed orientable surface can be made from a polygon with pairs of edges identified. A torus, for example, comes from a square where opposite edges are identified, top to bottom, left to right. If you glue the top and bottom edges of a square, you get a cylinder. Then glue the two circular ends of the cylinder together, and you get a torus. A genus 2 surface comes from an octagon with edges identified in the right pattern. These polygon constructions give you a concrete way to visualize the abstract surfaces, and they're also extremely useful for computing things like fundamental groups and homology groups. The fundamental group of the torus is the integers times the integers, two independent copies, corresponding to the two independent loops. The fundamental group of a genus G surface is generated by two G elements with one relation. These are all well understood, and they form part of a complete picture. Now, one thing worth pausing on is what orientable actually means. A surface is orientable if you can consistently define clockwise and counterclockwise on it everywhere. On a sphere or a torus, you can do this. Pick a notion of clockwise at one point, and you can transport it consistently around the whole surface without contradiction. On a Möbius strip or a Klein bottle, you can't. If you start with a notion of clockwise and carry it around the non-orientable loop, you come back with the opposite orientation. Clockwise has become counterclockwise. This has a physical analog. Imagine painting one side of a Klein bottle blue and the other side red. You can't. There's only one side. A sufficiently small insect walking on the surface of a Klein bottle would eventually find itself on what started as the other side without ever crossing an edge. Non-orientable surfaces have their own classification theorem too, using cross-cap number instead of genus. A cross-cap is like a Möbius strip with its boundary filled in, a disk where the identification is non-orientable. The real projective plane is a sphere with one cross-cap. The Klein bottle is a sphere with two cross-caps, and so on. Let's go up a dimension and talk about three manifolds, because this is where things get complicated and where the Poincare conjecture lives. A three-manifold is a space that locally looks like ordinary three-dimensional space near every point. You live in one, presumably. The universe is, as far as we can tell, a three-manifold. Locally, here in this room, in this solar system, in this galaxy, it looks like flat three-dimensional space. But globally, it might be curved, it might be finite, it might wrap around in some complicated way. The question is, what are all the possible three manifolds? This is enormously harder than the corresponding question for surfaces. For surfaces, we have a clean list: sphere, torus, and so on, classified by genus. For free manifolds, no such simple list exists. The world of free manifolds is much richer and weirder. One of the simplest three manifolds, other than the obvious three-dimensional Euclidean space, is the tree torus. Take a cube and glue opposite faces together. You end up with a space where if you walk far enough in any direction, you come back where you started. Like a video game where walking off the edge of the screen brings you back to the other side, but in three dimensions. This space is finite, but has no boundary or edge. It's a perfectly legitimate tree manifold. Another example is the tree sphere, the set of all points in four-dimensional space at a fixed distance from the origin. You can't visualize this directly, but mathematically it's well defined. It's the natural three-dimensional analog of an ordinary sphere. Now, back to Poincare's question. He asked, if a closed three-manifold has a trivial fundamental group, meaning every loop in it can be continuously shrunk to a point, is it necessarily a three-sphere? This sounds reasonable. For surfaces, the corresponding statement is true and easy to prove. A closed surface with trivial fundamental group is a sphere. But for three manifolds, it resisted every attempt for decades. In the 1960s, Stephen Smalley proved the generalized Poincare conjecture for dimensions 5 and above. This sounds backward. You'd think higher dimensions would be harder, but actually they're easier, because you have more room to maneuver when you're trying to slide things past each other. In 1982, Michael Friedman proved it for dimension 4. That proof was enormously difficult and introduced techniques that are completely different from what works in other dimensions. Friedman's result is a treasure of mathematics. Both Smale and Friedman won Fields medals for these results. And yet, the original case, dimension 3, the case Poincare himself asked about, remained open. It's one of the great ironies of mathematics. The harder versions got solved first. The attempt that came closest in the 20th century came from Richard Hamilton, an American mathematician who in the 1980s introduced something called Ricci flow. The idea is elegant and visual. You take a Riemannian metric on your manifold, a way of measuring distances and angles, and you let it evolve over time according to an equation. The Ricci flow equation is like a heat equation, but for geometry. It smooths out irregularities in the curvature, diffusing the curvature throughout the manifold the way heat diffuses through a conducting material. Hamilton showed that if you start with a 3-manifold with positive curvature everywhere, the Ricci flow smoothly deforms it until it becomes a round sphere. Beautiful. But the problem was singularities. Sometimes, during the flow, certain regions of the manifold develop infinite curvature. They pinch off, like a neck on a balloon being squeezed until it almost breaks. Hamilton couldn't handle these singularities in general, and the proof stalled. Then, in November 2002, a Russian mathematician named Grigory Perelman posted 3 papers on the Arxiv, an online preprint server where mathematicians post work before it's formally published. The papers described a complete proof of the Poincare conjecture. Perelman had been mostly off the grid for 7 years. He'd gone to the United States in the early 90s, met Hamilton, learned about Ricci flow, gone back to Russia, worked in near total isolation, and emerged with a proof. He didn't submit to a journal, he just posted it online and essentially moved on. Verifying the proof took years. Teams of mathematicians in the United States and China independently checked every step. By 2006, the community had confirmed that Perelman had solved it. The Clay Mathematics Institute had listed the Poincare conjecture as one of its 7 Millennium Prize problems, each worth $1 million. They offered Perelman the prize in 2010. He turned it down. He had also turned down the Fields Medal, the highest honor in mathematics, awarded to him in 2006. He reportedly said, in essence, that the prize wasn't fair because Hamilton had contributed so much with his Ricci flow program and that the mathematical community's response to other controversies around the proof had been disappointing. He withdrew from mathematics entirely and, as of the last public reports, was living with his mother in St. Petersburg. But what Perelman actually proved was more than just the Poincare conjecture. He proved Thurston's geometrization conjecture, a much bigger result, essentially a complete description of the possible geometries of 3 manifolds. Thurston, who won the Fields Medal in 1982, had conjectured that every closed 3-manifold can be cut along tori into pieces, each of which admits one of 8 possible geometric structures. Perelman proved this entirely. The result tells us something profound. The universe of 3-dimensional spaces is, in some sense, understood. We know what the pieces are and how they fit together. Now, let's step back and talk about the different branches of topology, because topology isn't one subject. It's more like a family of related subjects that grew from the same roots. The first branch is general topology or point set topology. This is the foundations layer, the language, the axioms, the basic definitions, open sets, closed sets, continuity, compactness, connectedness. Most of this was worked out between 1900 and 1940. It's taught in every graduate mathematics program in the world. It's the framework that everything else is built on. The second branch is algebraic topology. This is where you attach algebraic structures, groups, rings, modules to topological spaces, and then use algebra to answer topological questions. The idea is to build a bridge between topology and algebra. Topological problems are often hard, algebraic problems are often more tractable. So, you translate your topological problem into algebra, solve it algebraically, and translate back. The main tools of algebraic topology are the fundamental group, which Poincare invented, homology groups, and cohomology groups. Homology groups, which we touched on earlier, count holes of different dimensions. Cohomology is a dual version of homology that turns out to be even more useful in many settings. It has a natural multiplication structure called the cup product that encodes how the holes interact with each other. There's also homotopy theory, which is the deep study of continuous deformations called homotopies. Two maps between spaces are homotopic if you can continuously deform one into the other. The homotopy groups of a space capture its higher dimensional loops, loops of loops, loops of loops of loops, and so on. The homotopy groups of spheres are notoriously complicated and are not fully understood even today. A fiber bundle is a space that locally looks like a product of two spaces, but globally might be twisted. Think about a Mobius strip. Locally, it looks like a rectangle, a strip of the base circle times a short interval, but globally, the twist makes it different from a simple cylinder. Fiber bundles are everywhere in modern mathematics and physics. A vector bundle is a fiber bundle where the fibers are vector spaces. The tangent bundle of a manifold, where the fiber over each point is the tangent space at that point, is the most basic example. If you're on the surface of the Earth, the tangent space at each point is the flat plane tangent to the Earth at that location. The tangent bundle packages all these planes together into a single space. The Harry-Ball theorem is a beautiful result about vector bundles. It says you cannot comb a hairy ball flat without creating a cowlick. More precisely, there is no everywhere non-zero continuous vector field on the two-sphere. If you try to define a direction at every point of the sphere consistently and continuously, you'll always have at least one point where the direction is undefined, where the vector field has to vanish. This is a theorem about the topology of the tangent bundle of the sphere. The Harry-Ball theorem has a physical consequence. Any steady wind pattern on Earth must have at least one point of no wind, at least one calm eye where the wind stops completely. This is probably true because of topology. The Hopf vibration is another beautiful fiber bundle. It's a map from the three-sphere to the two-sphere, where the pre-image of every point in the two-sphere is a circle. All these circles, uncountably many of them, fill up the three-sphere, and any two of them are linked. It's one of the most beautiful structures in mathematics. A three-sphere decomposed into infinitely many circles, each linked with every other. The Hopf vibration appears in quantum mechanics, in string theory, and in the description of instantons in Yang-Mills theory. Characteristic classes are cohomology classes that measure the twisting of a fiber bundle. The Chern classes of a complex vector bundle, the Pontryagin classes, and Euler class of a real vector bundle. These are cohomology classes that obstruct the bundle from being trivial, untwisted. If all the characteristic classes vanish, the bundle is, in a certain sense, untwisted. Characteristic classes were developed by Stiefel and Whitney in the 1930s and by Chern and Pontryagin in the 1940s. The Atiyah-Singer index theorem, proved in 1963, gives a formula relating analytical quantities, the index of an elliptic differential operator, to topological quantities, characteristic classes. It's one of the deepest theorems in all of mathematics, connecting differential equations to topology, and it subsumes dozens of classical theorems as special cases. Algebraic topology was developed throughout the first half of the 20th century by people like Solomon Lefschetz, J. H. C. Whitehead, Heinz Hopf, Witold Hurowicz, and many others. One of the great achievements of mid-century mathematics was the development of the theory of fiber bundles and characteristic classes, which connected topology to differential geometry and eventually to physics. A fiber bundle is a space that locally looks like a product of two spaces, but globally might be twisted. Think about a Möbius strip. Locally, it looks like a rectangle, a strip of the base circle times a short interval. But globally, the twist makes it different from a simple cylinder. Fiber bundles are everywhere in modern mathematics and physics. The third branch is differential topology. This is a study of smooth manifolds. Manifolds where you not only have a topological structure, but also a notion of differentiation. You can do calculus on a smooth manifold. Differential topology asks about smooth structures. When does a manifold admit one? When do two smooth structures give the same manifold? One of the most stunning results in differential topology came from John Milnor in 1956. He showed that the seventh sphere, the sphere in 8-dimensional space, admits exotic smooth structures. There are exactly 28 different smooth structures on the seventh sphere, meaning 28 different ways to do calculus on it, all topologically equivalent but smoothly distinct. This was completely unexpected. Before Milnor, everyone assumed that a topological space had at most one smooth structure. Milnor showed this was wrong. Even stranger, in dimension 4, there are manifolds with infinitely many exotic smooth structures. Simon Donaldson, working in the 1980s and using techniques from physics, specifically gauge theory, and the equations describing the magnetic and electric fields in Yang-Mills theory, showed that four-dimensional manifolds have a wildly complicated theory compared to any other dimension. The dimension 4 world is special and weird. Differential topology is deeply connected to physics. The language of differential forms, objects that you can integrate over manifolds, is the natural language of electromagnetism, general relativity, and the standard model of particle physics. When Maxwell wrote down his equations for electromagnetism, and when Einstein wrote down the equations for general relativity, they were essentially doing differential geometry and differential topology without always calling it that. The fourth branch is geometric topology. This focuses on low-dimensional manifolds, 2, 3, and 4 dimensions, and their interaction with geometry. Knot theory lives here. The Poincare conjecture lived here. Thurston's work on 3 manifolds lived here. William Thurston himself, who died in 2012, was one of the great geometric topologists. He had an extraordinary geometric imagination. He could visualize things in 3 and 4 dimensions that most people can't even approach mentally. He completely transformed the study of 3 manifolds in the 1970s and 80s, introducing hyperbolic geometry as the dominant geometry of three manifolds. Most three manifolds admit hyperbolic structure and developing a rich program for understanding them. Now let's get into something that has a very low entry barrier but goes incredibly deep. Knot theory. Knot theory is the study of knots, and by knot, mathematicians mean something precise. A knot is a closed curve in three-dimensional space, a loop that doesn't cross itself. You can think of it as a piece of string with its ends glued together. Two knots are equivalent if you can deform one into the other without cutting the string. The simplest knot is the unknot, just a plain circle, no actual knotting. The next simplest is the trefoil knot, which has 3 crossings. Then there's the figure-8 knot with 4 crossings. As the number of crossings goes up, the number of distinct knots grows rapidly. Knot theorists have cataloged all knots up to around 20-something crossings, and there are billions of them. The big challenge is, given a knot diagram, a picture of a knot drawn on paper with crossings marked to show which strand goes over which, how do you tell whether 2 diagrams represent the same knot or different knots? This is harder than it sounds, because the same knot can look completely different when drawn in different positions. The answer is knot invariants, numbers or algebraic objects that you can compute from a knot diagram and that give the same value no matter which diagram you use for a given knot. If 2 knots have different invariants, they're definitely different knots. If they have the same invariants, they might be the same, or they might just happen to match on that invariant. The earliest invariant was the knot group, the fundamental group of the complement of the knot in 3 space. The complement is the space you get when you remove the knot from 3-dimensional space. 2 different knots can have very different complements. Then came polynomial invariants. Alexander discovered one in 1928. It's a polynomial, an expression in a variable t that you can compute from a knot diagram and that doesn't change when you deform the knot. The Alexander polynomial for the unknot is 1. For the trefoil, it's something different. Knots with different Alexander polynomials are different knots, but the Alexander polynomial isn't perfect. Some different knots have the same Alexander polynomial. It doesn't completely distinguish all knots. Then, in 1984, something extraordinary happened. Vaughan Jones, a New Zealand mathematician, was studying operator algebras, a part of functional analysis completely separate from knot theory, and he discovered a new invariant of knots, the Jones polynomial. It was stronger than the Alexander polynomial, distinguishing knots that the Alexander polynomial couldn't. Jones won the Fields Medal in 1990 for this discovery. But the really wild part is what Edward Witten did with it. Witten is a physicist at the Institute for Advanced Study. He's won the Fields Medal, the only physicist ever to do so. In 1989, Witten showed that the Jones polynomial has a natural interpretation in quantum field theory. Specifically, it's a certain path integral in a 3-dimensional quantum field theory called Chern-Simons theory. This was a revelation. A pure mathematical object invented by studying operator algebras turned out to be intimately connected to quantum physics. The bridge went both ways. Physicists could compute knot invariants using physics, and mathematicians could use the physics to discover new mathematics. More polynomial invariants followed. a polynomial independently discovered by several mathematicians in the 1980s and named after all of them: Hoste, Oknianu, Millet, Freid, Licorice, Yetter, Pshititsky, and Tratzek, and separately the Kaufman polynomial. And then in the 90s and 2000s came Kovanov homology, a categorification of the Jones polynomial, where instead of getting a polynomial, you get a whole collection of algebraic objects, groups whose structure contains more information than the polynomial alone. Mikhail Khovanov introduced this in 1999, and it's been a major area of research ever since. Categorification is a word worth spending a moment on. A lot of mathematical objects, numbers, polynomials, equations can be thought of as shadows of richer structures. When you categorify something, you replace numbers with groups or other algebraic objects, replace equalities with isomorphisms, and replace the operations with functors. The result has more information than the original, but is also more complex. The Jones polynomial assigns a polynomial to a knot. Kovanov homology assigns a sequence of groups to a knot. If you take the Euler characteristic of those groups, the alternating sum of their ranks weighted by degrees, you get back the Jones polynomial. So the Jones polynomial is the shadow of Kovanov homology. Why bother? Because the extra information in Kovanov homology distinguishes knots that the Jones polynomial can't, and it's a stronger invariant in other ways. It can detect whether a knot bounds a smooth disk in four-dimensional space, which the Jones polynomial alone can't. Categorification has become a major paradigm in modern mathematics. Geometric representation theory, which connects representation theory, algebraic geometry, and topology, is largely built on categorification ideas. The fundamental question of whether knot invariants can completely classify knots, whether there exists a complete invariant, is still open. We don't know. Knot theory turns out to be relevant to a surprising variety of things outside pure mathematics. Deoxyribonucleic acid is a good example of this. That molecule in your cells is enormously long. If you stretched it out from a single human cell, it would be about 2 meters, and it has to be packed into a cell nucleus that's only a few micrometers across. This packing creates knots and tangles. Enzymes called topoisomerases have the job of unknotting and untangling it so it can be replicated or transcribed. Understanding how these enzymes work, what moves they make, is a knot theory problem. The linking number of those strands, the types of knots that form during replication, these are all topological quantities. The topological state of the molecule affects gene expression and cell function. And some cancer drugs, like camptothecin, work by disrupting topoisomerase function. Topology is not metaphorically related to biology here. It is literally happening inside your cells right now. Let's spend some time on the algebraic side, because homology and cohomology are some of the most powerful and beautiful ideas in all of mathematics, and they deserve more than a quick mention. Homology starts with a simple intuition: holes. Every hole in a space corresponds to something you can't fill in. A one-dimensional hole is a loop that doesn't bound a disk, like the loop going around the hole in a torus. A two-dimensional hole is a sphere that doesn't bound a ball, like the surface of a hollow sphere itself, and so on. To make this precise, You build simplicial complexes, combinatorial approximations of spaces made from triangles, tetrahedra, and their higher dimensional analogs. You break your space into these pieces, set up formal sums of them called chains, and define a boundary operator that takes a chain and gives you its boundary. The kernel of the boundary operator chains with no boundary modulo, the image of the boundary operator chains that are themselves boundaries of higher dimensional chains, gives you the homology groups. This sounds technical, but the output is concrete and beautiful. The 0th homology group tells you how many connected components the space has. The first homology group tells you about independent loops, how many independent one-dimensional holes there are. The second homology group tells you about independent two-dimensional voids, and so on. For a torus, the first homology group is the integers times the integers, representing two independent loops, the one going around the hole and the one going through it. For a sphere, all homology groups above dimension 0 are 0, no holes at all. For a Klein bottle, the non-orientable surface, the first homology group is the integers plus the integers modulo 2, where the modulo 2 part reflects the non-orientability. Cohomology is the dual story. Instead of chains, you work with cochains, functions from chains to some coefficients. The co-boundary operator goes the other way. Cohomology groups are the result. What makes cohomology especially powerful is that you can multiply cohomology classes. Given two cohomology classes, you can form their cup product, another cohomology class of higher dimension. This multiplication structure, called the cohomology ring, encodes more information than homology alone. The cohomology ring is what Heinz Hopf used to distinguish certain homotopy types that homology alone couldn't separate. It's what Stiefel and Whitney used to study the topology of vector bundles. It's what Chern used to define characteristic classes, which are topological invariants of complex vector bundles. Characteristic classes appear throughout differential geometry and physics. There's also the realm cohomology, which approaches cohomology from the perspective of differential forms, smooth objects that you integrate over manifolds. Georges de Rham proved in the 1930s that for smooth manifolds, de Rham cohomology and singular cohomology give the same groups. This is a beautiful bridge between analysis, differential forms, integration, and topology, algebraic invariance of spaces. Let's talk about homotopy theory, which is where algebraic topology gets genuinely wild. Homotopy theory is the study of homotopies, continuous deformations between maps. Two maps from space X to space Y are homotopic if you can continuously deform one into the other. The set of homotopy classes of maps from X to Y is written X, Y, and it's one of the central objects in the subject. The homotopy groups of a space generalize the fundamental group. The fundamental group, also called the first homotopy group, is a group of homotopy classes of loops at a base point. The second homotopy group consists of homotopy classes of maps from a sphere to the space. The nth homotopy group consists of homotopy classes of maps from an n-sphere. For the circle, all homotopy groups above the first are trivial. The circle is simple in that respect. For a sphere of dimension 2, the fundamental group is trivial. Every loop can be shrunk, but higher homotopy groups are anything but. The second homotopy group of the two-sphere is the integers, with essentially one generator, the identity map. The third homotopy group of the two-sphere is also the integers, but for a weird reason discovered by Heinz Hopf in 1931. Hopf found a map from the three-sphere to the two-sphere that's topologically non-trivial. It's called the Hopf fibration. Every point in the two-sphere has, as its pre-image, a circle in the three-sphere, and these circles are linked in a specific way. The Hopf fibration is one of the most beautiful objects in mathematics. It shows up in physics too. It describes spinors, the mathematical objects used to describe electrons and other spin-half particles. The homotopy groups of spheres are still not fully computed. We know them in low dimensions and in what's called the stable range, where the groups stabilize as the dimension increases. But a complete description is a major open problem. The complexity of these groups grows in an apparently irregular way, with no obvious pattern. This is a place where topology runs into some of the hardest open problems in mathematics. Now let's talk about something more recent and more applied: topological data analysis, which took off in the 2000s and is now a major tool in science and engineering. The core idea of topological data analysis is that data has shape and shape has meaning. If you have a cloud of data points, measurements, gene expression levels, image pixels, whatever, and you want to understand its structure, you can ask topological questions about it. How many clusters are there? Are there loops in the data? Are there voids? The main tool is persistent homology. Here's the basic setup. You start with your point cloud. You want to build a topological space from it. So you start growing balls around each point, little neighborhoods all expanding at the same rate. As the balls grow, they start to overlap, and when they overlap, you connect the corresponding points with an edge. When three edges form a triangle, you fill in the triangle. When four triangles form a tetrahedron, you fill in the tetrahedron, and so on. You're building a growing sequence of simplicial complexes from your data, indexed by the size of the balls. As this complex grows, topological features appear and disappear. Connected components merge together. That's a cluster merging. Loops form and then get filled in. Voids appear and close. Each feature has a birth time when it first appears, and a death time when it gets filled in or merges away. You record all this as a persistence diagram or a persistence barcode. Features that persist for a long range of scales, born early and dying late, are likely to represent genuine structure in the data. Features that flicker in and out quickly are likely to be noise. By looking at the persistent features, you're extracting the topological shape of the data in a way that's robust to small perturbations. This is powerful because topology is naturally scale-free and coordinate-free. You don't have to choose a particular scale to look at your data. You don't have to define distances in a particular way. The topology will be stable under small changes to the data. Persistent homology was developed rigorously in the early 2000s with key contributions from Edelsbrunner, Lecher, Zomerodian, and Carlson. Gunnar Carlson, a Stanford mathematician, has been one of the most prominent advocates for applying topology to data, and he helped found a company, IASD, built around these methods. Persistent homology was developed rigorously in the early 2000s with key contributions from Edelsbrunner, Lecher, Zomerodian, and Carlson. Gunnar Carlson, a Stanford mathematician, has been one of the most prominent advocates for applying topology to data, and he helped found a company, IASD, built around these methods. The mapper algorithm, developed by Carlson and collaborators, gives another topological approach to data. Instead of computing full homology, mapper builds a graph, or higher dimensional network representation, of the data by covering it with overlapping patches, clustering within each patch, and connecting clusters that share points. The result is a topological skeleton of the data, a network that captures the global structure while compressing out fine-grained details. Mapper is more computationally tractable than full persistent homology and is very visual. The output is literally a graph you can draw and inspect. It's being used in many settings. Carlson's group used it to find the breast cancer subtype we mentioned. Researchers have used it to study the space of possible NBA player types, finding that the natural positions of basketball players are more complicated than the traditional 5-position model. Others have used it on functional magnetic resonance imaging data to map activity patterns in the brain. One thing worth appreciating about persistent homology is its stability theorem. The stability theorem, proved by Cohen, Steiner, Edelsbrunner, and Harrer, says that small perturbations to the data produce small changes in the persistence diagram, as measured by a specific metric called the bottleneck distance. This is not obvious. You'd worry that noisy data would produce wildly different topological features. The stability theorem says that doesn't happen. Features that are genuinely present in the data with long persistence will still be present under small noise. Short-lived features, which are likely noise, will stay short-lived. This gives the whole framework a rigorous statistical foundation. The applications have been remarkable. Researchers use topological data analysis to discover a new subtype of breast cancer. Carlson and collaborators analyzed gene expression data from breast cancer tumors using a topological lens tool called Mapper, which builds a network representation of data using topology, and found a cluster of patients with a specific mutation profile that had been missed by conventional methods. That subtype turned out to have near-perfect survival rates when treated correctly. Topological data analysis has been used to study neuroscience, the topology of brain connectivity, how neurons form loops and higher dimensional structures, how these structures change with cognitive load, and it's been used to analyze sensor networks, financial markets, material science, the structure of proteins, the shape of galaxies. One striking example is COVID-19. Researchers used topological methods to analyze the mutation space of SARS-CoV-2, identifying the topological structure of variant evolution and successfully predicting the emergence of new variants before they became dominant. The shape of the mutation data told you something about which mutations were coming next. In material science, topological data analysis has been used to study the packing of granular materials, the structure of amorphous solids, and the topology of porous materials. The porosity of a material, how its holes are connected, is literally a topological property, and topological data analysis gives you rigorous tools to quantify it. Now let's get into physics, because topology and physics have been in a remarkable relationship for the past several decades, and this is where things get genuinely futuristic. The story starts with Michael Berry in the 1980s. Barry was a British physicist studying quantum mechanics, and he noticed something strange. When you take a quantum system and slowly change its parameters, moving them around in a loop and returning to the starting point, the quantum state picks up a phase factor, a complex number that multiplies the state. You'd expect, maybe, that going around a loop and coming back should leave you unchanged. But no, you pick up this Barry phase, and here's the key. The Barry phase is topological. It depends only on the geometry of the loop in parameter space, not on how slowly you traverse it or any other details. It's a topological invariant. This was the first hint that topology was doing something physical in quantum systems. Then came the quantum Hall effect. This is an effect in two-dimensional electron systems at low temperatures and high magnetic fields, discovered experimentally in 1980 by Klaus von Klitzing. When you measure the electrical conductance of such a system, you find that it takes very precise values, exactly integer multiples of a certain quantity. The conductance is quantized. What makes this remarkable is how precise it is. The quantization is exact to 1 part in a billion or better, in real experiments with real samples that are nowhere near perfectly clean. The quantization is protected against impurities, defects, temperature fluctuations, all the things that normally mess up a measurement. The reason, worked out by Thulis, Komoto, Nightingale, and Dan Nyes in 1982, is topological. The integer that appears in the conductance formula is a topological invariant of the quantum state, specifically the Chern number, which is related to the curvature of the Barry phase over the space of crystal momenta. Because it's a topological invariant, it can't change gradually under small perturbations. It can only change if the topology changes discontinuously, that is, if there's a phase transition. This was a revelation. Topology was protecting a physical quantity from environmental disturbance in a way that no other mechanism could. The Chern number is named after Xin-Shen Chern, the great Chinese-American geometer who developed the theory of characteristic classes in the 1940s. Chern numbers are invariants of complex vector bundles over manifolds. They count certain kinds of twisting in the bundle. In the quantum Hall context, the relevant vector bundle is the bundle of quantum states over momentum space, and the Chern number of that bundle is what's being measured by the conductance. Pure, abstract mathematics, developed without any thought of physics, turned out to perfectly describe a real experiment done 60 years later. The fractional quantum Hall effect, discovered in 1982 by Tsui, Sturmer, and Gossard, is even more exotic. In this case, the conductance is quantized at fractional multiples of the basic unit. The fractions are not arbitrary. They appear in specific sequences: 1/3, 2/3, 1/5, 2/5, and so on. The explanation, developed by Laughlin and others, involves strongly correlated quantum states where the electrons behave collectively in ways that have no classical analog. The quasi-particles in these states carry fractional electric charge, not a whole electron's charge, but 1/3 of it, or 1/5. These fractionally charged quasi-particles have fractional statistics, they're enyans. And in certain filling fractions, they're non-abelian enyans, which means that exchanging them performs a matrix operation on the quantum state rather than just a phase shift. This is the physics behind topological quantum computing. David Thouless won the Nobel Prize in Physics in 2016, partly for this work. This opened the era of topological phases of matter. Topological insulators, topological superconductors, topological semimetals. These are materials whose electronic properties are fundamentally protected by topology. A topological insulator is a material that is insulating in its interior. Electrons can't move freely through the bulk, but conducting on its surface. The surface conductance is protected by topology. As long as certain symmetries of the material are intact, the surface states can't be destroyed. You could add impurities to the surface, and the conductance would persist. This isn't magic, it's topology. Bismuth selenide, bismuth telluride, mercury telluride, these are some of the real materials that behave as topological insulators. They're being studied intensively for potential applications in electronics and quantum computing. And that brings us to topological quantum computing, which is perhaps the most exciting frontier, where topology meets technology. Quantum computers are powerful because they use quantum mechanics, superposition, and entanglement to perform computations that classical computers can't do efficiently. But quantum computers have a fatal weakness: decoherence. The quantum states you're trying to preserve are incredibly fragile. Interactions with the environment, vibrations, stray electric fields, thermal fluctuations destroy the quantum coherence you need. Quantum error correction is the conventional approach to this problem. You redundantly encode information across many qubits, and you actively monitor and correct errors. But this requires enormous overhead. You might need thousands of physical qubits to implement one reliable logical qubit. Topological quantum computing is a completely different approach. The idea, proposed by Alexei Kitaev in 1997, is to encode quantum information in a topological way, so that local perturbations literally cannot disturb the information. The information lives in global, topological properties of the state, and a local disturbance can't change a global topological property. The particles you'd use are called anyons. Regular particles come in two types: bosons and fermions. When you exchange two bosons, the quantum state doesn't change. When you exchange two fermions, the state picks up a minus sign. Anyons are different. They live only in two spatial dimensions, and when you exchange them, the state picks up an arbitrary phase, or even undergoes a matrix transformation. The history of how you braided the anyons around each other is encoded in the state. This is where knot theory comes back in. The braiding of anyons through time traces out a path in spacetime that is a braid. The quantum computation is encoded in which braid you perform. And because the quantum amplitude depends only on the topological type of the braid, not on the exact path, the computation is automatically robust against local errors. Non-abelian anyons are the kind you'd actually want for topological quantum computing, the ones where the exchange operation is described by a matrix, not just a phase. Fibonacci anyons, Ising anyons, these are the candidates. They haven't been definitively realized in experiments yet, though there's been progress with Majorana fermions, which are their own antiparticles and which appear at the ends of certain topological superconducting wires. Microsoft has been betting heavily on Majorana-based topological qubits. In early 2023, they published results claiming signatures of topological superconductivity, then retracted a related earlier paper after errors were found. The field is advancing, but it's honest about how difficult this is. Whether topological quantum computing will be the path that works, nobody knows yet, but the physics is real and the potential is enormous. Let's now talk about topology and the universe. What cosmology and theoretical physics say about the possible shape of space itself. Einstein's general relativity tells us that space is not flat. The matter and energy in the universe curve space, and that curvature is what we experience as gravity. But general relativity describes the local geometry of space, how curved it is near each point. It doesn't determine the global topology of space. Think about it this way. A flat rubber sheet and a cylinder can both have flat geometry locally, no intrinsic curvature, but they're topologically different. The cylinder has a loop in one direction that you can't shrink. The flat sheet doesn't. Locally, you can't tell them apart. Globally, they're different. So the question of the topology of the universe is separate from the question of its geometry. The universe could be flat locally, as observations suggest the universe appears very close to flat, but have a non-trivial topology globally. It could be a three-torus, where walking far enough in any direction brings you back to your starting point. It could be some other three-manifold entirely. Cosmologists have looked for signatures of non-trivial topology in the cosmic microwave background, the afterglow of the Big Bang. If the universe were a three-torus with a size comparable to the observable universe, we'd expect to see specific patterns of matching circles in the background radiation, places where we're seeing the same region of space from different directions. These searches haven't found anything convincing yet. Either the universe is simply connected trivial topology, or its topological scale is larger than we can observe, or both. It's also possible that the universe has more dimensions than the three spatial ones we see. String theory, the framework that attempts to unify gravity and quantum mechanics, requires 10 or 11 dimensions. The extra dimensions are hypothesized to be compactified, rolled up into tiny spaces too small to observe directly. The topology of these extra dimensions determines the low-energy physics we observe. Different topological choices give different particle content, different force strengths, different cosmological constants. This is the string landscape, the enormous space of possible universes, each corresponding to a different topological choice for the compactified dimensions. The topology of the extra dimensions is, in string theory, not just a mathematical curiosity. It's the structure that determines why the universe looks the way it does. Now, let's zoom back out and look at some of the places topology is being used and developed right now, because the subject is very much alive. One place is machine learning and artificial intelligence. Topological deep learning is an emerging area that uses topological structures, not just graphs or grids, but simplicial complexes and hypergraphs as the underlying data structures for neural network architectures. Standard graph neural networks process data on graphs, nodes connected by edges. Topological neural networks process data on higher dimensional structures, triangles, tetrahedra, and so on, capturing higher order interactions between data points. This turns out to matter for molecular biology, because molecules are naturally described by higher order interactions. The interaction of three atoms in a molecule isn't reducible to pairs of interactions. It's a genuinely three-way relationship. Topological neural networks can capture this more faithfully. In neuroscience, researchers are finding that the brain processes information using structures that have rich topological organization. Groups of neurons form simplicial complexes whose topology evolves as the brain processes stimuli. There are topological transitions in neural activity correlated with perception and cognition. The homology groups of neural activity patterns tell you something about what the brain is doing. The Blue Brain Project, a large European effort to build a detailed simulation of the rodent brain, found topological structures in simulated neural circuits that correspond to specific cognitive functions. The topology of the connectivity, not just the strengths of the connections, matters for function. In robotics, topology shows up in configuration spaces. The configuration space of a robot is the space of all possible positions and orientations the robot can take. Planning a path for the robot from one configuration to another is a topological problem. The path has to avoid obstacles, and the set of valid configurations might have complicated topology, with holes corresponding to forbidden regions. Topological methods can find qualitatively different classes of paths and ensure coverage. In fluid dynamics, the topology of flow fields matters. The Poincare-Hopf theorem, a classical result in topology, relates the topology of a surface to the structure of vector fields on it. Specifically, the sum of the indices at singular points of the field, the places where the field is zero, equals the Euler characteristic of the surface. This puts constraints on where eddies and vortices can appear in fluid flows on curved surfaces. In condensed matter physics, topological phases continue to be discovered. Beyond topological insulators and superconductors, there are topological semimetals, Weyl semimetals, quantum spin liquids, and fracton phases, the latter being a particularly exotic new type of topological order discovered in recent years, where certain excitations literally cannot move by themselves and require collective action to move. Now let's look at some open problems. Topology is a mature field in some ways, but there are still massive open questions. One is the smooth, four-dimensional Poincare conjecture. Perelman solved the topological version, showing that every simply connected topological three-manifold is homeomorphic to the three-sphere. But for smooth four-manifolds, the analogous question is open. Is every smooth four-manifold that is homotopy equivalent to the four-sphere diffeomorphic to the standard four-sphere? No exotic smooth four-spheres have been found, but nobody has proved they can't exist. Another is the classification of four manifolds. We have a complete classification of surfaces, and we have some results for three manifolds, thanks to Thurston and Perelman, but four manifolds are not classified. Donaldson's work in the 80s showed that four manifolds are wildly more complicated than other dimensions, with exotic smooth structures appearing in abundance. Gompf and Stipsik's book on four manifolds is full of exotic examples, but a complete classification, anything like what exists for surfaces, seems enormously far off. The Curvaire invariant problem about the framing of high-dimensional manifolds was solved only in 2009 by Hill, Hopkins, and Ravenel, using methods from stable homotopy theory, a particularly deep and modern branch of algebraic topology. The solution was a surprise even to many experts. The smooth shown flies problem in dimension 4, whether every smooth embedding of a 3-sphere in the 4-sphere bounds a smooth 4-ball is open. In every other dimension, the answer is yes. The Andrews-Curtis conjecture about group presentations is equivalent to a statement about 3-dimensional topology and remains open, and the homotopy groups of spheres remain incompletely computed. We know stable homotopy groups where the groups stabilize as dimension increases in a range, and there are computational methods that push further, but a complete description seems out of reach. Let's talk about some theories and speculations about where topology might lead us. One of the most intriguing ideas is that spacetime itself might be topological in nature, that the smooth manifold picture of spacetime in general relativity might be an approximation, and the true structure at very small scales, the Planck scale, about 10 to the power of negative 35 meters, might be combinatorial or simplicial. Loop quantum gravity, one of the approaches to quantum gravity, describes spacetime as a network of spin foams, combinatorial structures with topological properties. The geometry of spacetime in this picture emerges from the combinatorial structure rather than being assumed from the start. If this is right, then the topology of spacetime at microscopic scales is physically meaningful. There might be tiny topological handles or wormholes connecting distant regions. There might be a discrete structure underlying the smooth manifold of spacetime. Another speculation, the phenomenon of quantum entanglement might be related to topology. When two particles are entangled, making a measurement on one instantly affects the other, regardless of distance. Some researchers have proposed that entanglement corresponds to a kind of topological connection, a wormhole between the two particles. This is the ER equals EPR conjecture. Einstein-Rosen bridges equal Einstein-Podolsky-Rosen pairs, proposed by Juan Maldacena and Leonard Susskind in 2013. If true, this would mean that entanglement and geometry are deeply connected, and topology would be at the heart of quantum gravity. In topological quantum computing, the hope is that non-abelian anyons can be reliably created, braided, and measured. If this happens, it would give us a qualitatively new type of quantum computer, one whose error protection is, in principle, guaranteed by physics rather than by engineering. The knot theory of braids would literally be running the computer. There's also a theory, still speculative, that the brain might be using topology in a more fundamental way than just as a description of neural connectivity. If quantum effects play a role in cognition, an idea proposed by Penrose and Hameroff, among others, though very controversial, then topological quantum states might be relevant to how we think. Let's talk about something that comes up in topology that most people have never thought about: the topology of function spaces. Not just spaces of points, but spaces where each point is itself a function. The space of all continuous functions from one topological space to another with a suitable topology is itself a topological space. This might sound abstract, but it's extremely useful. For instance, the space of all closed curves on a manifold, loops that might or might not be contractible, is a topological space. Studying the topology of this loop space is a major area of homotopy theory. The free loop space of a manifold is related to string theory, where strings are one-dimensional objects tracing out loops. The homology of the free loop space encodes information about closed geodesics, the natural closed curves on a Riemannian manifold, analogous to straight lines. Morse theory, developed by Marcin Morse in the 1920s, is a way of understanding the topology of a manifold by studying smooth functions on it. The idea is simple and powerful. Take a smooth function on a manifold, height above sea level, for example, on a mountainous landscape. The critical points of the function, the peaks, valleys, and saddle points, are where the topology changes as you raise the sea level. Each type of critical point corresponds to a topological change. Peaks add cells, valleys take them away, saddle points do something in between. Morse theory tells you how to build the manifold up from its critical points. And by counting critical points of various types, you get inequalities called the Morse inequalities, relating the number of critical points to the Betti numbers of the manifold, which are the ranks of its homology groups. For example, you need at least as many saddle points as there are independent loops. If the manifold is complicated topologically, you're forced to have many critical points. Morse theory was used by Stephen Smale in his proof of the high-dimensional Poincare conjecture. Smale introduced the H-cobordism theorem, which under certain conditions allows you to cancel pairs of critical points and simplify the manifold. In high dimensions, 5 and above, this cancellation is always possible in the simply connected case, leading to the proof. The same strategy doesn't work in dimensions 3 and 4 because you don't have enough room to maneuver. Modern Morse theory, called Floer theory, replaces finite dimensional manifolds with infinite dimensional function spaces and replaces the gradient flow of a smooth function with the solutions of a partial differential equation. Andreas Floer used this in the late 1980s to define invariance of 3 manifolds and knots. After Floer's death in 1989, his ideas were developed by many others and became central to modern low-dimensional topology and symplectic geometry. There are some remarkable theorems in topology that deserve mention even if we can't go deep into them. The Brouwer fixed point theorem says that any continuous function from a disk to itself has at least one fixed point. If you take a map, crumple it up, and throw it on the table somewhere inside the original uncrumpled map, there is always at least one point on the crumpled map that lies directly above the corresponding point on the flat map. This sounds surprising, but follows from a beautiful topological argument. The Borsuk-Ulam theorem says that for any continuous function from the n-sphere to n-dimensional Euclidean space, there exists a pair of antipodal points directly opposite each other on the sphere that are mapped to the same point. In dimension 2, applied to Earth. At any time, there are 2 antipodal points on Earth's surface with exactly the same temperature and exactly the same atmospheric pressure. The Jordan curve theorem says that any simple closed curve in the plane divides it into exactly 2 regions, an interior and an exterior. This sounds obvious. Of course, a circle divides the plane into inside and outside, but proving it rigorously is surprisingly hard. The theorem was proved by Camille Jordan in 1897, though his proof had gaps, and a fully rigorous proof came later. For wiggly, fractal-like curves, the intuition that this should be obvious is much less compelling. The ham sandwich theorem says that given any number of objects in n-dimensional space, there's a hyperplane that simultaneously bisects all of them. Two objects in 2 dimensions. There's always a single line cutting both exactly in half. 3 objects in 3 dimensions. Always a single plane cutting all 3 in half simultaneously. This follows from the Borsuk-Ulam theorem applied cleverly. These results have a flavor that's very typical of topology, a statement that seems like it should be obvious but turns out to require serious work, or a statement that seems surprising but turns out to be true for clean reasons. Let me also spend some time on higher category theory and homotopy type theory, because these represent where topology is going as a foundational discipline. Traditional mathematics is built on set theory. Every mathematical object, a number, a function, a space, is ultimately a set. Functions between sets are maps. The equality relation on sets is binary. Either 2 sets are equal or they're not. Homotopy type theory, developed in the 2000s and formalized most prominently by Vladimir Voevodsky, reimagines foundations using topology. The key idea is that the notion of equality should be understood as a path. 2 objects are equal if there's a path between them. And because paths can themselves be homotoped to other paths, equality of equalities is a thing, and so is equality of equality of equalities, and so on. This creates a hierarchy of homotopy levels, and the different levels have different mathematical meanings. Points are in dimension 0. Paths between points are in dimension 1. Homotopies between paths are in dimension 2, and so on. The topological language turns out to be exactly right for capturing subtleties of equality in mathematics that set theory fumbles. In set theory, you identify isomorphic objects and move on, but the identification is informal. In homotopy type theory, isomorphisms are paths, and the act of identifying isomorphic objects is a mathematical operation with a precise meaning. Voevodsky used this insight to design a proof assistant, a computer program that can check mathematical proofs based on homotopy type theory. This led to the Unimath project, an ongoing effort to rebuild parts of mathematics in a way that can be formally verified by computer. The vision behind this is significant. If mathematics could be done in a framework where every proof is machine checkable, then the long tradition of human errors in mathematics, flawed proofs, gaps undetected for decades, claimed results that turned out to be wrong, could be dramatically reduced. The history of topology includes famous examples. Poincare's own initial claim, various purported proofs of the Poincare conjecture that turned out to be wrong. Machine verification won't make mathematics less creative, but it could make it more reliable. One more piece worth understanding is the relationship between topology and symmetry, which runs throughout the subject. A Lie group is a group that is also a smooth manifold. It has both an algebraic structure, you can multiply elements and take inverses, and a geometric structure. The circle, the one-dimensional sphere, is a Lie group, you can add angles. The three-sphere is also a Lie group, corresponding to the quaternions of unit length. The orthogonal group, the unitary group, the special orthogonal group, all Lie groups. Lie groups are the symmetries of physics. The standard model of particle physics is built entirely from Lie groups. The circle group for electromagnetism, the special unitary group of rank 2 for the weak force, the special unitary group of rank 3 for the strong force. Einstein's general relativity has the diffeomorphism group, the group of smooth coordinate changes, as its symmetry. The topology of Lie groups matters for physics. The fact that the rotation group, the special orthogonal group in 3 dimensions, has a non-trivial fundamental group, specifically the group of loops in it is the integers modulo 2, is what's responsible for the existence of spinors. Electrons don't transform as plane vectors under rotation. They transform as spinors, which pick up a minus sign under a 360-degree rotation. This isn't a physical coincidence. It follows from the topology of the rotation group. The covering spaces of Lie groups are closely related to their representations. The spin groups, which are the simply connected covering groups of the orthogonal groups, are what you need to describe particles with half-integer spin. The whole theory of spin in quantum mechanics is a topological statement about the rotation group. Hermann Weyl, in the 1920s, worked out the representation theory of compact Lie groups, how these groups act on vector spaces, and his results are topologically flavored throughout. The Weyl character formula, which computes the characters of representations, involves a topological object called the Weyl group. The geometric Langlands program, one of the deepest programs in contemporary mathematics, is about the representations of Lie groups and their connections to the topology and geometry of moduli spaces. In data science, the integration of topological methods with machine learning is still in early stages. As models get larger and data gets more complex, topological invariance may become a crucial tool for understanding what neural networks are actually learning. The topology of the learned representations, the structure of the lost landscapes, the homological properties of the data. There's a conjecture in topological data analysis that hasn't been fully proved, that there exists complete topological invariance for certain classes of data, meaning invariants that uniquely characterize the shape of a dataset up to some notion of equivalence. Proving this would be both a mathematical achievement and a practical win for anyone doing topological data analysis-based analysis. The study of symplectic topology, the topology of spaces with a symplectic structure, which is a type of geometry without distance but with a notion of area, has seen major advances in recent decades. Connected to Hamiltonian mechanics, string theory, and mirror symmetry. Floer homology, a tool developed by Andreas Floer in the late 80s, is a powerful invariant of symplectic manifolds that has led to solutions of classical problems in symplectic geometry. Floer died tragically young, at 34, but his ideas have been central to the field ever since. Contact topology, the odd-dimensional cousin of symplectic topology, has seen similar advances. The Weinstein conjecture that every contact manifold has a closed Reeb orbit was proved for many cases by Hofer and collaborators, and completely proved in 3 dimensions by Taubes in 2007. Let's think about what all of this might add up to in the coming decades. The most immediate area of impact is probably topological quantum computing. If Microsoft or another group manages to reliably demonstrate non-abelian enyans and topological braiding operations, the consequences for computing would be enormous. Topological qubits would be error-protected by physics, changing the resource requirements for fault-tolerant quantum computation dramatically. We'd be looking at quantum computers that could actually run the algorithms that make quantum computing interesting. Shor's algorithm for factoring, Grover's algorithm for search, quantum simulation of molecular systems for drug discovery and materials design. In material science, topological materials have already led to the prediction and discovery of new phases of matter that could be useful in electronics. Topological semimetals have exotic transport properties. Topological superconductors might host Majorana modes useful for quantum information. We're likely to see continued discovery of new topological phases, some with properties we haven't anticipated. In biology, topological data analysis is going to become a standard tool in genomics, proteomics, and neuroscience. The ability to extract shape-based signatures from high-dimensional biological data, the topology of gene expression landscapes, the topology of protein folding pathways, the topology of evolutionary trees, will complement and sometimes outperform conventional statistical methods. We'll probably see topological data analysis routinely used in drug discovery, where understanding the topology of molecular interaction networks could guide the design of new therapeutics. In pure mathematics, the interaction between topology, number theory, and algebraic geometry through schemes and motives is an active frontier. Grothendieck's program of motives, a hypothetical universal cohomology theory for algebraic varieties, is still incomplete, but tremendous progress has been made. The Langlands program, one of the grandest unifying visions in mathematics, connects number theory, representation theory, and geometry, and topology runs through all of it. The development of higher category theory and homotopy type theory, which uses the homotopy theory of spaces as a foundation for all of mathematics, is ongoing. Univalent foundations, introduced by Voevodsky before his death in 2017, is a reimagining of the foundations of mathematics where identity itself is a topological concept. Two objects are the same if there's a path homotopy between them. This is being implemented in computer-proof assistants, building toward a future where mathematical proofs can be machine verified. If that works, and the early signs are promising, it could change how mathematics is done. Proofs could be certified by computer. Errors in long complex arguments could be caught mechanically. The kind of 100-year mistakes that happened with the Poincare conjecture, where Whitehead thought he had a proof and didn't, could become impossible. Let me try to tie some threads together here. Topology started with a practical puzzle about walking across bridges in a Prussian city. It grew by noticing that some problems, like Euler's bridge problem and his formula for polyhedra, are really about shape and connection, not about measurement. Through the 19th century, it accumulated examples: Mobius strips, Klein bottles, Riemann surfaces, the Cantor set. Poincare gave it wings in 1895, inventing the tools of algebraic topology and asking the questions that drove the field for 100 years. The 20th century built out the foundations rigorously, created the major branches, and answered progressively harder questions. Milnor found exotic spheres. Smale and Friedman solved high-dimensional versions of the central problem. Thurston understood three manifolds. Donaldson found exotic four-dimensional phenomena. And then Perelman, in 2002, solved the hardest remaining problem in geometric topology, turned down $1 million and a Fields Medal, and walked away. Meanwhile, topology was connecting to everything else, to physics, through Berry phases, quantum Hall effects, topological phases of matter, to quantum computing through anyons and topological error protection, to data science through persistent homology and topological data analysis, to biology through the topology of molecular structures and protein analysis. The reason this keeps happening, the reason topology keeps showing up in places you wouldn't expect, is that topology is, in some deep sense, the study of what doesn't change. Topology looks for the invariants, the things that survive deformation and perturbation. And in a noisy, complicated world, whether that's a quantum computer fighting decoherence, or a biologist trying to understand gene expression data, or a physicist trying to find order in the possible states of matter, the things that don't change are the most informative things. You don't care how exactly the coffee mug was molded, or what its precise dimensions are, or whether it's chipped. What you care about is, does it have a hole? Because that's what makes it useful as a mug. That sounds like a silly example, but it's the deep principle. In quantum computing, you don't care about the exact path the anion took. You care about the topology of the braid, because that's what the quantum computer actually computes. In materials, you don't care about the exact positions of every atom. You care about the topological phase, because that's what determines whether the surface conducts electricity. Topology is the mathematics of the things that can't be undone by small mistakes. That turns out to be incredibly powerful. One last thing before we wrap up. We've talked about all the results and applications of topology, but I want to take a moment to say something about what it's like to actually do topology. There's a kind of thinking that topology demands that's different from most mathematics. Geometric intuition matters enormously. The ability to visualize objects in 3 and 4 dimensions, to feel what a manifold does when you deform it, to see why two spaces are or aren't homeomorphic. But that intuition has to be disciplined, because geometric intuition fails. Your gut says things that are flat out wrong, sometimes spectacularly so. Exotic smooth structures on the 7th sphere. 4 manifolds with infinitely many distinct smooth structures. A knot invariant that comes from quantum field theory. A proof of the Poincare conjecture using a heat equation for geometry. Topology is full of results where the right idea comes from somewhere completely unexpected, where the tools of physics solve a problem in pure geometry, where the study of abstract nonsense about loops and holes turns out to predict the behavior of real materials. This is why Poincare wrote essays about mathematical creativity and the unconscious mind. He noticed that the right mathematical ideas often come not from conscious effort, but from letting the problem sit, from looking sideways at it, from bringing in tools from somewhere completely different. Topology, more than most fields, rewards this. If you want to go deeper into topology after this, here's a rough road. Start with point set topology. A book like Munkres, which is dense but clear, will take you through the foundations. Then move to algebraic topology. Hatcher's book is freely available online and is the standard modern text for geometric topology and three manifolds. Thurston's notes are available online and are written in his unique visual style. For differential topology, Milnor's Topology from the Differentiable Viewpoint is one of the most beautiful short books in all of mathematics. And if you want applications, the topological data analysis community has produced a lot of accessible material. The Ripser software package and the GUDI computing library make it easy to compute persistent homology. There are online courses on topology in condensed matter from leading universities. The bridge problem in Konigsberg was demolished in World War II. The city is now Kaliningrad, part of Russia. Only 5 of the original 7 bridges still exist, but it doesn't matter. The question that came from that city still echoes through mathematics, physics, biology, and computing. A question about walking across bridges became a question about the shape of everything.